Everybody, welcome to this afternoon's session. This is AIM414, how to optimize your LLM with NKI. My name's Scott Perry. I'm a solutions architect on the Annapurna Labs team at AWS, where we work directly with customers on our AI/ML accelerators, Trainium and Inferentia. And joining me today, I have my colleague.
Hey everyone, this is Sadaf. I'm also a solutions architect at AWS Trainium. I'm primarily focused on AI/ML performance on Neuron. And we both are super excited to have you here today for this session.
Yeah, thanks for coming out. So this is a code talk, so we're going to spend most of the session digging into a terminal editor and code editor, running some scripts and doing all of this live, so hopefully it goes well. But before we do that, we do have to just go through a few background slides just to give everybody an idea of what Neuron and NKI is all about. So bear with us just for a few slides, and then we'll get right into it. So to give you some context, for many years, customers have been doing machine learning workloads on AWS. And some of the early feedback that we got from customers is that they wanted some choice, and they wanted to see improved price performance for running their ML workloads on AWS. So back in about 2019, we actually invested in designing a purpose-built machine learning accelerator that we would offer via EC2 instances in AWS. And that first generation was called AWS Inferentia. So this is Inferentia 1 if you're used to the EC2 instances. And this was a smaller accelerator designed for the deep learning models of the time. This was kind of like BERT and YOLO and that sort of thing. Since then, we've actually released the second generation, Inferentia 2. And maybe more interestingly, we've also released 3 versions of the AWS Trainium chip, with the third generation launching just yesterday. So AWS Trainium is actually a more powerful chip, capable of being used for distributed training as well as inference. So at the heart of the Trainium and Inferentia accelerator chips are the Neuron cores. So in a given instance, you might have multiple chips, and within each chip, you can actually have multiple Neuron cores. So today, we're going to be working with a TRN2 instance. It actually has 8 physical cores within the chip. We're going to be using one of them for the examples here today. But within that core, this is a high-level schematic of what's actually involved. So what's really interesting about this architecture is, as I mentioned, it's purpose-built for machine learning workloads. So if you see, we have 4 specific compute engines within the Neuron core. Starting with the tensor engine, this is focused on things like matrix multiplications and transposes. We have the vector engine that you can use for max pool, average pool type layers. There's the scalar engine for things like activations. And we also have a general purpose compute engine with general purpose cores that can be reprogrammed for maybe layers that aren't covered in the other 3 engines. So here we have 4 compute engines that you can actually use in parallel on this chip to maximize compute utilization. Also worth noting here is we have a couple on-chip SRAMs. You see the SBUF and the PSUM. So these are obviously on-chip, so they're very close to the compute, offering high bandwidth, but maybe lower capacity. We have a DMA, or a set of DMA engines for moving data, and we also have high bandwidth memory as part of the device. And because these are offered via EC2, we also have access to the host memory. In this case, it would be DRAM associated with the CPU. So I'll call it, there's 3 levels of the memory hierarchy that we care about, right? There's that on-chip SRAM. This is the lower capacity but very high bandwidth memory that we would love all of our data to live on all the time if it could. We also, at the bottom of the tiers, have the host memory, which is high capacity but lower bandwidth. And in between, we have, a bit of a compromise, which is the HBM, moderate capacity and pretty good bandwidth. And one of the major struggles when you're trying to optimize your machine learning workloads is, how do you place data, get it as close to the compute exactly when you need it, and how do you juggle moving between the tiers otherwise? And when we talk about optimizing machine learning workloads, one way of kind of representing a given workload is the roofline model. Has anybody seen a roofline model before? Okay. Just take a quick refresher then. So as part of the roofline model, basically for any given algorithm, any given machine learning, say, model, there's going to be an arithmetic intensity intrinsic to that model, like an algorithmic arithmetic intensity. So you can basically, whatever the mathematical operations are for that given model, it's going to consume, and there's going to be a certain amount of operations that you have to do per byte of memory that's read. But for a given accelerator chip, you're going to have a finite memory bandwidth, and you're going to have a finite, maximum compute throughput that you can achieve. And if it turns out that your achieved arithmetic intensity for a given workload falls on the left-hand side, meaning that there's low ops per byte, you're going to be memory bound. And we don't really want to be there, because if we're in that case, it means that we're limited by the how fast we can read from memory for the workload that we're actually operating. What we would like to do is try to push things to the right-hand side of the graph and be compute-bound, meaning that we're doing many ops per byte of memory read, so we can take full advantage of the compute accelerators. So the difference between algorithmic, kind of theoretical arithmetic intensity and achieved is basically the implementation, right? So how can we improve performance and kind of shift the graph to the right? So we can do things like pipelining operations. So if you have a major workload, sometimes you can chunk it up into smaller bits and actually run multiple parts of the workload at any given time and keep the engines a little busier than they would be otherwise. There's things like minimizing data movement. So if you're doing a lot of DMAs, moving a lot of data unnecessarily at the wrong time, that's also going to reduce your performance. So we want to try to avoid that. We want to maximize data throughput. So in some cases, you might be sending small messages or moving small bits of data around. Is there some way maybe we can coalesce that into larger chunks and improve data throughput? And if we're in a distributed setting, we might have multiple Trainium chips that we need to communicate across sometimes. So say synchronizing gradients during training. And when that happens, it would be nice if we could overlap the collectives with some type of compute or data movement, so we're not just sitting there waiting for the collectives to take place. Okay, so this is why and maybe how we would try to improve performance, but what does it mean for Trainium and Neuron? Like, how do we get there? So to work with the Trainium and the inferential chips, we have the Neuron SDK, and this is the software development kit that includes all of the various layers of the stack. So we have a compiler, runtime, driver, and user tools that allow customers to work with Trainium and inferentia. And we typically look at our customers as three personas. We have ML developers, data scientists, and performance engineers, and lots of folks kind of fall between the lines. But for today, we're focused more on the performance engineer persona. And within the Neuron SDK, we have a certain set of tools that are going to be applicable to performance engineers. So the one that we want to focus the most on today is called the Neuron Kernel Interface, NKI. Has anybody worked with NKI before or heard about it? Okay, awesome. So what is NKI? So NKI is essentially a Python-based domain-specific language for writing kernels for Trainium and inferentia. So before we had NKI, basically you could write your machine learning model maybe in PyTorch and JAX, run it through the Neuron compiler, which takes the compute graphs from your model, optimizes them to run on Trainium or inferentia, and then you could run your model that way. But you were putting a lot of faith in that the general purpose kind of Neuron compiler was going to perfectly optimize your model. And as we see with our accelerators and other accelerators, oftentimes customers need a lower level access. They want to be able to really fine-tune the model to take full advantage of the underlying hardware. And that's what NKI offers you. So if you're familiar with OpenAI Triton, this is not quite Triton. This is a little bit different, but this is our kind of flavor of writing low-level kernels for our accelerators. So it integrates directly with PyTorch, JAX, and NumPy. It directly emits Neuron ISA instructions, so the actual hardware instructions that exist on the chips get emitted from this platform. And we have a couple namespaces within NKI. We have the NKI lang, which is higher level constructs to help you out, helper functions, that kind of thing. But we also have direct Neuron ISA instructions as part of the NKI ISA namespace. And on the left-hand side, you do see a kernel. We're going to actually hop into that in a minute here and go through line by line and show you what it's like to build a basic kernel before we get into the actual benchmarking and whatnot. Okay, so for today's session, what are we looking to achieve here in record time? We're going to start off, we want to start by benchmarking and profiling an LLM. In this case, it's going to be Qwen 3. So we're going to run that using Hugging Face transformers and the Neuron SDK. So it's going to compile the basic Qwen implementation to run on Trainium as is, using naive attention. That's just going to be our baseline. So we'll look at the performance and look at a basic profile. Then Sadaf's going to walk us through an actual NKI kernel implementation of attention. He's going to add that into the Qwen 3 model that we had previously run, and we're going to redo the benchmarking and the profiling to see what the performance gains hopefully are at the end of the session. And then we'll obviously give you guys some time for questions at the end. And the technology stack we're using specifically here today, so we're using AWS Trainium 2, the second generation of our chip. On a smaller instance, we're going to be using one of the Neuron cores out of 8 that exist on the chip today, just to kind of keep things a little bit more consumable. We're going to be using the Neuron SDK to both compile and run our models. In our case today, we're using Qwen 3 0.6b an embedding model, and this is available via the Hugging Face Transformers library. Okay, so with that, why don't we just take a quick look at that example kernel that I put on the slide in a code editor. We'll go through it, and then we'll get right into the benchmarking and show you that vanilla implementation. Okay. Awesome. Okay, so here we can see a very basic kernel. In this case, it's called NKI tensor add kernel. This is just a basic kernel that takes two similarly shaped tensors, and it does element-wise addition of them. The first thing I want you to notice here is it's just defined as a basic Python function, right? So the only thing that's really special about this function is that we decorate it with niki.jit, just to let the Neuron compiler know that this is basically intended to be a NKI kernel that we want to compile. And there's a specific constraint around the NKI kernels today. So the inputs and the outputs, you can see the A input, B input, these are the two tensors that will be added, as well as the output. These need to exist on HBM, right? So we talked about the three kind of tiers of memory that we're going to be focused on. The input and outputs actually have to exist on the on-device memory, but not on the on-chip SRAM. And the framework is going to handle that for us, so we'll be using PyTorch today. So if we just run through kind of line by line what this is doing, we pass in two inputs that we want to add together. There's a basic check to make sure they're the same shape, otherwise the element-wise addition won't work. And here we're going to see there's a similar flow that exists in all NKI kernels. So the first step is we need to allocate some space on the on-chip SRAMs. So here we're allocating some space for both the A input tensor and the B input tensor using this sbuff.view. And sbuff is one of our on-chip SRAMs. And the next step is we actually use an ISA instruction. This is a DMA copy, where we specify that we want to copy from the A input and B input HBM tensors to the on-chip tensors. Okay? And similarly, we actually do something similar. We allocate some space for the result. In this case, we call it ctile. And again, this is on sbuff. We use sbuff.view to allocate the space for the tensor. And then we use the ISA tensor instruction to actually do the addition for us. So here you can specify that this tensor op is using the addition operator. The two inputs are the two tiles that we had basically passed in and copied to SRAM, and then we're outputting the results to the destination, which is the C tile. And then lastly, because we need to get the outputs back to HBM to return back to the framework, we use HBM view to allocate an HBM hosted tensor, and then again we use a DMA copy to get the results back to HBM before we return the result. So again, this is a bit of a trivial kernel just to kind of give you the high-level flow, but you can see that this is fairly low level for if you've been used to working with PyTorch and whatnot. But if you're really looking to squeeze the best bang for buck out of your model and make the best use of the hardware, there's going to be cases where you might need to actually get this deep into the space. Okay, with that, let's take a quick look at the benchmarking script here. So I didn't want to just blindly run a script, so I am going to run through the code a little bit with you here just to show you what we're running. But this is just a basic Python script. It uses Hugging Face Transformers and the Qwen3 model. And essentially, we load the Qwen3 model on CPU first. We're going to compile it for Neuron, and then we're going to run a bunch of inferences and kind of time the latency and measure the throughput that way. And we'll also do a sanity check against CPU to make sure that the model results are the same as CPU. Okay, so if we skip over the imports, there's a little bit of environment setup that we use for Neuron for the runtime. In this case, we want to specify that we're just using a single core, for example. We're also, because we're going to be doing some profiling, we enable some profiling enabling environment variables here just to make sure that we capture the metrics that we need. Okay, so we do wrap the model in a basic class here. This is just to make it a little bit easier to get the last hidden state from this embedding model, just to kind of make things a little bit easier for the demo today. But the class, you can see it doesn't really do anything other than do a forward pass with the outputting only the last hidden state. We also have a helper function that encodes some example text and returns a repeating tensor based on the batch size that we specify. So it's just going to be the same text kind of repeated over and over based on the batch size that we need just to help us out. And we have a few arguments that we use to control the behavior of the benchmark script. Obviously, like controlling things like batch size and max length. It's nice to be able to tweak that as you're doing the executions. But we also have a NKI flag here that we use to specify whether or not the benchmarking script should use the NKI implementation that Sadaf is going to add for us a little bit later. Okay, so here you can see this is where we actually load the model for the first time onto CPU. We do truncate the model to 4 layers here just to speed things up and get this done in 45 minutes here today. But essentially, the performance for a handful of layers should be similar to the performance for the full model. You just have to scale it up accordingly. Okay, and if we skip down a little bit here. So this is where we actually get into the meat of it. So if we've previously run the script for this configuration, we're going to cache the Neuron compiled model on disk just to save time in case we want to run it again. But if it isn't compiled, we use this torch neuronx.trace call. And this is what actually triggers the Neuron compiler to take the code. In this case, it's just the vanilla implementation of Qwen3 with naive attention. It's going to pass that into the Neuron compiler. The Neuron compiler will extract the graphs, compile them to run on Neuron using the example inputs that we've provided, and it returns a PyTorch loadable model that we can then save to disk, and we cache it out to disk. Okay, so if we haven't compiled it, we compile it, and if it's already on disk, we just load it in. We do a quick warm-up inference. We run through an iteration of 5 inferences, measuring the inference time, and then we calculate the accuracy compared to CPU, and output the results. Okay, so it should be pretty straightforward if you've worked with Hugging Face before, but again, I just wanted to show you the code so it wasn't a mystery. And why don't we actually run this and get into the heart of it here. Okay, so if you open up the terminal, here I'm logged into a TRN2 3XL instance, and we have a Neuron SDK environment already available to us, right? So we can run commands like Neuron ls, for example, to get a quick breakdown of what's available on this instance type. But let's just run the benchmarking script here, Python. Okay, and what we should see is that it detects that the previous CPU outputs are saved on disk to save time, and it loads those, and it also loads the pre-compiled Neuron model for us, again, just to save a couple minutes. And within a few seconds, we should start to see this executing the model on the Neuron core. So again, this is Qwen3 0.6b. It's a 4-layer version of that model using a 16K sequence length. Okay, and it's just about done running. And now we get the accuracy, just to prove it to you. So the MSE loss and both the cosine similarity are what we would expect. So the outputs of this Neuron compiled model that didn't run on CPU, it actually ran on the accelerator. They 100% match the CPU outputs, which is great. But on the performance side, you can see that this is not a very performant model out of the box, right? We're only getting 0.35 prompts a second with latency around 3 seconds. So I think there's definitely room for improvement there. And one of the areas where we often look to improve performance for transformer models is the attention block. So we'll take a look at that shortly. But before we do that, I did want to show you that we can actually look at the profiling results that we captured here as well. So sometimes what you'll see is that maybe you're actually getting great device time, like the model's actually running well on Trainium, but there's something else going on at the PyTorch layer that's slowing things down. So if we get a system level view, a system profile here, we'll be able to see, did this model actually run kind of the best we could expect for right now before we add NKI. So as part of the Neuron SDK, we do have Neuron Profile, which is the profiling tool. There's different interfaces for this. Today, we're just going to output the system level profile in a Perfetto compatible format so that we can quickly load it up in Perfetto, which is an open source visualization tool that you're probably familiar with. So we'll do Neuron Profile View. We specify the directory that contains the profiling data, and we'll tell it to use output format Perfetto. Okay. And now if we look in the directory, it's created the system profile for us, so we'll just quickly download that. And let's hop into the browser. And this is Perfetto. Has anybody used Perfetto before for any kind of? Okay, awesome, so you're familiar. Yeah, so we'll just open up the trace file. And we'll take a quick look here. Awesome. So if you're not familiar, this is just showing the execution timeline starting on the left, kind of scrolling to the right. You can see the first thing that happened, there's NRT load. This is actually the Neuron runtime loading the weights of the model into HBM. And then beyond that, you see all these NRT execute calls. And what's nice is we can actually see exactly what's happening within the Neuron runtime. So here it's executing the model. You can see there's basically 7 executions in the model here. So our benchmarking loop was 5, but we also did 1 execution for the accuracy check and 1 as a quick warm-up. so that's why there's 7. But if we click on any of these executions, you can actually see some metadata associated with the execution, which for this model maybe not that interesting, but for a larger model or maybe an execution where you had multiple graphs executing on different cores, this would be very helpful. So here we can see the exact name of the graph, which is the compiled version of the model for Neuron, and we can see which neuron core it's running on, those sorts of things. And on the left-hand side, you can see the duration of the execution is pretty much what we saw from our benchmarking script. It's just under 3 seconds execution latency, which is, I'd say not great. So hopefully we can improve on that. But yeah, with that being said, this is the baseline performance. So we did take that original Qwen3 model from Hugging Face, we compiled it to run on Neuron, we executed it on Trainium and got those baseline results. And now let's see if Sadaf can improve on that using NKI.
Sure. Thanks, Scott. Thanks for setting up the stage. Hey, everyone, this is Sadaf again. How many of you have lunch already? Oh, man, so sorry. Not a good time to talk about the code after lunch. But I promise you, we will try to make it as exciting and promising as possible. Just bear with us. What we are trying to do here essentially is, as we have seen performance for this Qwen3 model, we got the performance numbers and we got the timeline as well. And we'll try to see if NKI, which is neuron kernel interface, as Scott mentioned, can help us to improve this performance. So in this part of the talk, we are going to focus on 3 major objectives. Number 1, I would like to show you how quick and convenient it is to integrate NKI kernels in our existing model codes. Number 2, what are the performance impact of the same? And number 3, which is going to be more like food for thought, like from the extensibility and applications point of view, is there a way we can use those NKI kernels in our respective workloads when we go back home? So these are the 3 major objectives that we are going to address in this part of the talk. Are you with me? We're going to do a little bit of code. As I promised, I'll try not to make it very boring for you, but we'll do our best. We good? Awesome. All right. So there are a couple of things that I think it's worth noting from the profiling that we have done so far. We see like for each iteration, it's taking approximately 2 seconds, 812 milliseconds. On a rough basis, we can just say it's 3 seconds. Are you able to hear me there? Awesome. That is one. Second, as Scott was trying to show, the throughput that we are seeing here is 0.35 prompts per second. So technically, it means that it takes approximately 3 seconds to just process 1 prompt. We're good? So when we are talking about NKI, and as Scott mentioned, like how does it help us to improve the performance? And the reason it can do that, because it works at the very low level, which is very close to the hardware, and it takes care of all the optimizations that are available on the table so that we can get the maximum performance from the underlying hardware, which is Trainium in this case. So we are very proud and excited about that. Yesterday, we have launched a NKI library, which Scott is going to talk about in a minute. And we are exposing some of the kernels, predefined, pre-implemented kernels, which can be plugged into your models, just like we're going to say in this Qwen3 model, and we can just take advantage of the performance on Trainium. So let's have a look at that. People who have worked with Hugging Face Transformers library before, we would know for each model directory, we have different model-specific files. So in case of Qwen3, we have configuration file here, we have modeling file, modular file, and so on. The very first file that I'm super interested in right now is this modeling file. Let me try to make this screen a little bit better. Sorry, there's a question? We'll talk about that, yes. So the reason I am interested in this modeling Qwen3 file, because this file essentially, which is given by Hugging Face Transformers library, tells us the complete implementation of Qwen3 model, right? If I want to understand what the RMS norm look like for Qwen3, it is here. If I want to understand what MLP looks like for Qwen3, it is here. And how the rotary embedding looks like, or how is it implemented, everything is here. And one part that we are super interested today is attention. Everybody heard about transformer-based models? Everybody heard about attention, right? So that's what we are going to see today. We have this eager attention forward method that has been provided by the Hugging Face Transformers library itself for this model. And what we are going to do is we are trying to see if there's a way we can replace this with NKI attention, right? And we will see what is the performance implication of the same. So that is one module that we are going to be super interested in today. What I'm going to do is, I'm going to take this attention, eager attention forward here, and I'm just going to paste it. Everybody can see the code, right? Do I need to maximize it? Are we good? Awesome. So I just copy-pasted that eager attention, and let's give it a meaningful name. Let's call it like NKI attention forward, right? And I'll not touch the input arguments, but I'm going to, of course, get rid of this implementation because we are going to write our own implementation here. And we will return the attention output, and because it's inference, we don't need to return the weights. So we're good. Step number one of my objective is to showcase how easy and convenient it is to integrate NKI kernels in our existing models. That's what we are going to look at right now. So we have this attention forward.py file here, and what it has, we can go into the detail in a minute, but what it has is, it has the implementation, the NKI implementation for different flavors of attention, right? So as we know, like we have SDP attention, we have sliding window attention, we have flash attention, and so many other variations of that. It has the implementation for majority of those profound attention mechanisms. And we are going to use one of them. In this case, we are going to leverage flash attention for Qwen3. So what this file does, what this implementation file does is, on top of that, it provides me kind of an adapter, or you can just think of like an interface function. And what it does is, it will take all the inputs from me. It will try to make sure basic hygiene, like I'm giving the right shapes, formats, data types, and then it will invoke the right kernel for us. We definitely are going to look into that kernel as well. But before that, let's invoke this kernel from our modeling Qwen3.5. All right. So my attention output will be coming from here, and I'm going to call this one. But as we were looking at it, and we can go through this provided documentation as well, because it's a NKI implementation of the kernel, it expects us to provide the QKB tensors in a specific format or specific shapes, right? Because very close to the hardware, it expects us to do that little bit of massaging, reshaping before, and then give those tensors back to NKI so that it can perform its operations. So for that, we need to make a little bit of reshaping for our QKB tensors right now. So for query, first thing what I'm going to do is, we know if I expose the shape of my query, or key or value in this case, I will get the bed size, number of heads, sequence length, and head dimension. That's what it's going to give it to me. This kernel, the attention kernel, it expects the query. I'm going to write it as a comment here so that we keep the track of it. So it says, OK, you are in this format right now, but I expect you to give me the query in this format. Just a little bit of reshaping, permute, and all these classical NumPy operations that we are going to perform here. OK? So what we are going to do is, from BHSD to B times H ds, essentially we are contracting 2 dimensions to 1 dimension, and then changing the sequence of SD and DS. That's it. So what we can do is, first of all, we can do a permute to switch S and D, or swap the sequence length and the head dimension. So we will make it first BH ds, and then I think it will be easy from there to make it B times H ds. So let's do that. So query equals to query.clone dot permute. And the reason we are doing it, because we need to change the shapes, the sequence of the shapes, BHSD to BHDS. So 0 will remain 0, 1 will remain 1, 2 will become 3, and 3 will become 2. So far, good. So we have achieved BHDS. And then we will reshape it to B times HDS, as simple as that. And we will ask to give us contiguous memory location so that it's optimized. Fair enough? We just reshaped our query tensors. That's it. Now, similarly, we can do the same for key tensors as well. So our key is exactly in the same shapes. So we just need to make the change to my tensors names here, key states, and everything remains same. For values, it's even simpler. For values, it says, give me B times H as D. So we don't need to do the permute here. We can simply just reshape. And then, since we don't have to permute, we can keep the S and D at their original positions. Fair enough? And once we have this, it means I am ready to provide these tensors to this adapter kernel. And I'm going to call this so we can provide our query, key states, value states, and then scaling. Yeah. And yeah, just change the variable names. Thank you. So that it's not key, it's values. Fair enough? So what we have done so far, we have changed our QKV shapes. That's it. Did not make any changes to the tensor values, did not make any other changes, just reshape them in the format that this kernel expects. Once we do that, we would be able to call this attention through NKI, passing out our parameters, and we'll get the attention output. Once we get the attention output, the beauty of it that it's going to give us attention output in this format, and we would like to have it in the final outcome should be in this format, BSHD. So we need to do the exactly same magic here as well. So we can do. So first of all, we are going to reshape it so that it becomes BHSD. And then we just need to swap S and H, right? So right now we have HS, then we're going to make it SH. So we will just call our favorite function, which is transpose. And then we will transpose the first index with second index, contiguous. All right? Awesome. And then we return the attention output. If we look at the implementation of this, we have just swapped query, key, values, not swapped, but reshaped. And once we have reshaped them, we have called the attention kernel, getting the output, again reshaping it in the expected format that the function output requires, and then using it. Another thing that we have to do is we have to switch, because there is a place where we are calling the attention here. What I have done here is I have already added this, like if my config has the NKI as an attention implementation, call NKI attention forward. So we are switching from eager attention to NKI attention so that we are 100% sure that we are calling the right attention. Fair enough? So let's quickly have a look. I'm going to remove the previous profiles. As we have seen when Scott was running, he was able to get the profiles. I'm going to delete it so that we don't have any cached data or something. And then we will try to make it run as well. So let's have our terminal open. And this time, I'm going to call the same script which Scott has run, but this time I'm going to pass this argument, right? So hope it runs. First time. Let's do it. What is going to happen now is, because it has found a new attention, it's going to submit the model again for the Neuron compiler. Hey, I got this new attention, just compile it for me so that I can run on Trainium, right? So this compilation will take maybe a couple of minutes. Meanwhile, it's taking a couple of minutes. Let's have a quick look at the actual attention kernel that I promised to you. So I'm again going to the attention forward pi. And here, if we look at our adapter kernel, I will save all these details for you. You can check it out later. But what essentially I can see, it's calling this attention kernel implementation without swapping. I am more interested to find out where's the definition of this kernel. So here it is, line number 657. And just to warn you, it's pretty decent implementation. It's like 1,000 lines of code. So I don't want you to bore with that. But what I want to share with you is that, because at the end of the day, attention is nothing but a function of QKVs, essentially, right? We are doing QK transpose, softmax, and then multiplying this with V, right? So this is exactly what it is doing, but it is doing in a very hardware-aware fashion. What it means with NKI, we have this amazing capabilities that we can take the maximum advantage of the underlying hardware, which is Trainium. So what it does is it employs various memory as well as compute optimization techniques. And when I'm saying memory optimization techniques, it uses smart DMAs just to ensure like we are efficiently using the DMA engines. We are efficiently using the DMA packet sizes as well. It uses the intelligent tiling concepts. It uses the efficient memory layout and allocations. When it comes to compute, what it's going to do is it takes the advantage of pipelining so that, as Scott was mentioning in one of the slides, where we have different compute engines, it makes sure that it is trying to keep all the compute engines as much busy as possible in parallel so that we can utilize at like whatever the available compute that we have on the table, we can take the best out of that. It also uses the concept of op fusion, like when we are fusing or kind of combining multiple operations together so that we don't have to do a lot of DMAs or a lot of memory accesses, we can keep our compute engines more and more busy. So it employs all these mechanisms to get the best performance from Trainium. And once you employ all these mechanisms, what you get is a super optimized implementation of your model or a specific module that you're talking about that, right? So after a couple of minutes, we see the compiler status is passed. Now it's going to run the inference with this new attention implementation. Remember, it's not running the naive attention anymore. It is running the NKI attention this time. Fair enough? And this time, the performance that we see is 2.99 prompts per second. Can anybody remind me what was the performance that we have seen with the naive attention? Exactly. 0.35 to almost 3 prompts per second. So we are talking about like approximately like 6 to 8 times better performance. Not 6 to 8%, 6 to 8x performance boost here. Isn't it amazing, right? So let's have a look at the profile as well. So just like Scott has generated the profile, we are going to generate the profile again. We are going to download this system profile. And this time we are going to save it with, let's say, NKI. We go to the Perfetto again. Remember this time as well, Scott was mentioning 2 seconds, 812 milliseconds, approximately 3 seconds, right? Now let's open this NKI trace this time, which we have just got. And let's expand it a little bit. And let's see the time. Are we ready for that? Now, if we go there, the duration from almost 3 seconds to almost a quarter of a second. Right? So The point I'm trying to drive over here is that with this performance, with this NKI kernel, we are getting almost 6 to 8x performance boost right in front of us. And that was my second objective. First was to showcase how easy it is to integrate a NKI kernel. That's what we have done. And what is the performance implications or performance boost that we get out of it. The third objective that I was trying to drive is a food for thought. Think about it. It is just a small model with just one attention module or attention part of the model that we have replaced with NKI. Now, this model has much more than that. It has MLPL also, which is super compute bound. It has QKV projections, output projections, and so on. And Scott will drive us in a moment. He'll help us to understand, like, we have some of these kernels exposed to the outside world, first time ever. These are the production scale kernel that we can use in our own models and leverage this amazing performance boost. So again, going back to the performance gain, from throughput, for the naive attention, we got this one-story building to almost 10-story building now. And from the latencies point of view, which we want to be as small as possible, we have come down from there to here. Yeah, sorry, please. Do we have the profile of what? I don't think we do profiling based on the power consumption as of today. Yeah. So with that, I'll leave the floor for Scott. He'll drive us home from here. Thank you.
Awesome. Thank you, Sadaf. So as you saw, guys, we were able to go from not so great performance to pretty impressive performance gains, basically just by adding a few lines of code and taking advantage of a kernel that's been built essentially by the Annapurna team. What we're really excited to talk about, though, is just yesterday we launched NKI Library. So this is an open source project. It contains a number of pre-optimized NKI kernels that are written by our team, curated, tested, and maintained by our team and provided on GitHub. So starting off, there's a number of kernels available there today. You can grab the QR code and take a look. So there's a lot of dense model support kind of in the beginning now. We're going to add additional models around, or additional kernels around mixture of experts and other use cases and workloads as well. But this is super exciting because up until now, NKI's still in beta, but it gives customers this access to the lower level compute engines that you just didn't have before, right? So you saw the naive implementation of Quen. When we compiled it, it did run, it gave accurate results, but the performance was really lackluster out of the box. But with NKI, we were able to drastically close the gap there and really drive amazing performance with this model. And again, we focused on attention today, but there's a lot of other aspects of different models, different layers that you might be able to apply NKI to. And it's a little bit like onion peeling, right? Like you're going to get into a workload, you'll do a device level profile, figure out where the bottlenecks are. Maybe you tackle some of those with NKI. It moves the bottleneck somewhere else, right? And at some point, you almost chase it forever. But at least with NKI, it puts the capabilities to the customer's hands that you can actually do this performance engineering that just wasn't possible from the PyTorch level before. So awesome. With that, I want to thank everybody for coming out today. We really appreciate you coming in for an afternoon session to learn about Trainium and NKI. We have a number of other Neuron and Trainium sessions today and tomorrow if you're interested in checking them out. And we're open for questions. Thank you.
All right. Thanks, folks.